Have you ever noticed how quickly we skip past the planets that are most like home? In school, the rocky Tellurian worlds, Mercury, Venus, Earth, and Mars, often show up as a simple list: size, distance from the sun, a few fun facts, and then we move on. But hidden behind those basic charts are questions we rarely hear. Why did one planet keep its oceans while another boiled them away? Why did one world grow life while its neighbor dried into rust and dust? Tonight, here on Fall Asleep with Science, we're going to slow down and stay with these four worlds a little longer. If you enjoy calm, curious journeys through familiar space that suddenly feels new, a quick like and subscribe helps others find their way here too. For now, settle in and let's explore what your textbooks left out about the Tellurian planets. Most people recognize the name of the first planet in our solar system, Mercury. It has been visible in the sky since ancient times and was named after a Roman god. Humanity has known about this small world for thousands of years. It is not hidden in darkness. Because it orbits so close to the sun, it is flooded with intense sunlight. Even so, among the rocky Tellurian planets, Mercury is the least explored. In all of spaceflight history, only 2 robotic missions have flown past or orbited it. That is a surprisingly small number. It raises a fair question. Is Mercury simply uninteresting, or is there more to it than we were taught? To understand why Mercury matters, it helps to look at its basic physical nature. Many people picture it as a small, hot rock near the sunday. That image is not completely wrong, but it leaves out important details. When we look at real images taken by spacecraft, Mercury at first can feel a bit like our moon. The surface is covered in craters and broad plains. But there are differences. In true color, Mercury is not just a flat set of gray shades. There are subtle browns and slightly reddish tones, signs of different materials and a more complex surface history than it seems at first glance. Inside, Mercury is even more unusual. Scientists estimate that the planet is made of roughly 70% metal and 30% silicate rock. In other words, compared with the other rocky planets, Mercury is more metal than stone. This unusual mix gives the planet a very high density. Its average density is about 5.427 grams per cubic centimeter. That is only slightly lower than Earth's density of about 5.515 grams per cubic centimeter. If Mercury were the same size as Earth, this density would give it almost the same surface gravity as our own planet. But Mercury is much smaller, so its gravity at the surface is weaker. The surface gravity on Mercury is about 3.7 meters per second squared. If you compare that to Earth, where the surface gravity is about 9.8 meters per second squared, you would weigh a bit more than 1/3 of your Earth weight on Mercury. Interestingly, this gravity is only slightly lower than the gravity on Mars, even though Mars is a much bigger world. That illustrates how dense Mercury really is. Before leaving the topic of size, it is helpful to compare Mercury to some of the large moons in our solar system. Ganymede, the largest moon of Jupiter, and Titan, the largest moon of Saturn, are both bigger in diameter than Mercury. If you place them side by side, Mercury would actually be the smaller one in terms of physical size. However, their masses are much lower than Mercury's mass. Again, because Mercury is so rich in metal and so compact. Looking more closely at the surface, you can see how this small planet has aged. Mercury's face is covered with many impact craters and broad, dark plains that astronomers call mare regions, similar to the Maria on the moon. This pattern tells us that Mercury has been geologically quiet for billions of years. It does not have active plate tectonics or widespread volcanism today, but it was active in the distant past. One clear sign is the presence of many long, narrow ridges that stretch across the surface. These ridges, sometimes hundreds of kilometers in length, are thought to be scar-like cliffs formed as the planet's interior cooled and shrank, wrinkling the crust. One of the most striking features on Mercury is a huge impact basin known as the Caloris Basin. It is about 1,550 kilometers in diameter. At some point in the distant past, a massive object hit Mercury and gouged out this enormous crater. The energy of that impact was so great that it triggered volcanic eruptions. Lava flooded the basin and later cooled, and a ring of raised terrain more than 2 kilometers high formed around the impact site. On the opposite side of the planet, at the point directly opposite the Caloris Basin, lies a region of strange, jumbled hills, often called weird terrain. When you compare this area to other parts of Mercury, the difference in texture is obvious. Many scientists think the shock waves from the Caloris impact traveled through the planet and disrupted the crust on the far side, creating that unusual landscape. Conditions at the surface of Mercury are extreme. One of the most dramatic features of this environment is temperature. Because the planet is close to the sun and has almost no atmosphere, the surface temperature varies a lot from place to place. Near the equator, on the side facing the sun, the surface can reach about -73 degrees Celsius, up to over 400 degrees Celsius. At the poles, though, the temperature never rises above about -93 degrees Celsius. Without a thick atmosphere to spread out heat, the equator and pole regions are very different. This strong variation is also linked to Mercury's unusual orbit and the way it rotates, which we will come back to soon. The point directly under the sun, called the subsolar point, can reach about 400 degrees Celsius. On the night side, where the surface faces away from the sun, temperatures can drop to around -163 degrees Celsius on average. Since Mercury is small and hot and its gravity is not strong enough to hold on to a thick atmosphere for long periods of time, any gas around it slowly escapes into space. As a result, Mercury cannot keep the heat it receives during the day. The day side bakes, and the night side cools dramatically. Even so, Mercury is not completely bare of gas. It has what scientists call an exosphere, a very thin envelope of atoms and molecules around the planet. In an exosphere, the particles are still held by the planet's gravity, but the density is so low that the particles rarely collide with each other. That means it does not behave like the kind of gas we are used to in normal air. From the viewpoint of a spacecraft, this exosphere can sometimes be seen as a faint glow or cloud around the planet. Spacecraft, like NASA's Messenger probe, have given us direct images and measurements of this exosphere. When the solar wind, a constant flow of charged particles from the sun, strikes Mercury, it can knock atoms out of the exosphere and even off the surface. These atoms then stream away into space, forming a thin tail behind the planet, stretching away from the Sunday. Many planets, including Earth, have some form of this kind of tail. Although it is usually very faint, Earth has its own exosphere too, but it begins about 600 kilometers above the ground, in the region where the atmosphere slowly transitions into space. For Mercury, the exosphere is not stable or permanent. Atoms are constantly being lost to space and replaced by new atoms. These replacements come from several sources. The surface itself, which can release atoms when hit by solar radiation or micrometeorites. The solar wind, which can implant and then remove particles, and possibly gases from the planet's interior. The detailed balance of gain and loss is still an active research topic. Despite its harsh environment, Mercury also holds some surprising materials. Observations by NASA have confirmed that some craters near the North Pole contain water ice. These craters are in permanent shadow, where sunlight never reaches the floor. In those dark, cold traps, temperatures stay low enough to preserve ice for very long periods of time. This is a striking result, given that the same planet has regions hot enough to melt lead. Another key feature that sets Mercury apart from Mars and many other small bodies is that it has a global magnetic field, or magnetosphere. Mercury's magnetic field surrounds the planet and interacts with the solar wind. It is much weaker than Earth's field, only about 1.1% as strong, but it is still significant. This magnetic field is able to deflect a portion of the incoming solar wind, shaping the space environment around the planet. Mercury's path around the Sun is also special. It has the most eccentric, or stretched out, orbit of all the planets. The distance between Mercury and the Sun ranges from about 46 million kilometers at its closest point, called perihelion, to about 70 million kilometers at its farthest point, called aphelion. This change in distance affects both the amount of sunlight Mercury receives and its orbital speed. Mercury takes about 88 Earth days to complete one full orbit around the Sun day. Its rotation, however, is not simple. Mercury is locked into what is called a 3-to-2 spin-orbit resonance. This means the planet spins 3 times around its own axis for every 2 orbits it makes around the Sun day. One full rotation on its axis, its sidereal day, takes about 59 Earth days. By coincidence, this is almost exactly half of Mercury's synodic period with respect to Earth, which is about 116 days. The synodic period is the time between 2 similar alignments of Mercury and Earth, with the Sunday between those alignments. Mercury completes exactly 2 rotations on its axis. This numerical coincidence caused confusion in the past. For a long time, astronomers believed that Mercury was tidally locked to the Sun, always showing the same face to it, the way the Moon always shows the same face to Earth. Mercury orbits very close to the Sun, which makes it hard to observe for much of its orbit. Only at certain times does it appear far enough from the Sun in the sky to be seen clearly through telescopes. In those favorable times, early observers would study the visible surface and note its features. When they looked again, about 118 days later, during another good viewing period, they saw nearly the same face again. It seemed to confirm that one side of Mercury always faced the Sunday. What they did not realize then was that during that interval, Mercury had rotated exactly twice. Only later, with radar observations that could track the rotation directly, did scientists learn that Mercury spins slightly faster than it orbits. This 3-to-2 resonance leads to a very unusual experience of day and night on the surface. For an observer standing on Mercury, the time from one sunrise to the next, called a solar day, is equal to 2 Mercury years. From the surface, the sun's motion in the sky would look particularly strange. The sun would rise relatively quickly above the horizon. As it approached midday, it would seem to slow down, then even appear to move backward for a while, before continuing forward again and finally setting. One full cycle of this apparent motion would take 1 Mercury year for the daytime and another for the nighttime. In other words, the night would last as long as a year. The reason the sun appears to pause and move backward is tied to the change in Mercury's orbital speed. About 4 Earth days before perihelion, the speed of Mercury along its orbit around the Sun becomes equal to the angular speed of its rotation. At that moment, the Sun seems to stand still in the sky. At perihelion itself, Mercury's orbital speed is greater than its rotational speed. so the sun appears to drift backward. About 4 days after perihelion, Mercury's rotation once again dominates, and the sun resumes its normal westward path across the sky. From a view above the planet, looking down on its orbit and rotation, you would see the sun's apparent motion speeding up, slowing down, pausing, and reversing twice during a single solar day at some latitudes. Mercury's orbit is also tilted compared with Earth's orbit. Its orbital plane is inclined by about 7 degrees relative to the plane of Earth's path around the Sunday. Because of this tilt, we only see Mercury pass directly across the face of the sun in what is called a transit. When Mercury is exactly between Earth and the sun, and also happens to be at the right point in its inclined orbit, this geometry does not line up very often. As a result, these transits occur only about once every 7 years, on average. Another detail of Mercury's orientation is its axial tilt. The axis of rotation is almost perfectly upright relative to its orbital plane. The best measurements give a tilt of only about 0.027 degrees. This is even smaller than the axial tilt of Jupiter, which is about 3.1 degrees. With such a tiny tilt, Mercury has almost no seasons in the way we experience them on Earth. Finally, it is worth remembering our own place in relation to this small world. For Mercury, Earth is just a bright point in the sky. In one image taken several years ago by the Messenger spacecraft, Earth appears as only a few pixels across. At that moment, except for those not yet born, every person alive on our planet was contained within that tiny speck of light. To understand how we were able to see Earth and Mercury in this way, it helps to look at the spacecraft that made those observations. That spacecraft was called Messenger, and its story is closely tied to the problem of how to reach Mercury at all. When humans first began sending probes beyond Earth, attention went to other planets first. Venus, our closest planetary neighbor, was visited in 1962. Mars followed in 1965, and Jupiter in 1973. Mercury was not reached until 1974. That order may feel surprising. The closest distance between Earth and Mercury is about 77 million kilometers. On average, Mercury is actually the closest planet to Earth. The closest distance between Earth and Jupiter, by contrast, is about 588 million kilometers, roughly 8 times farther away. Yet Jupiter received repeated visits, again in 1974, twice in 1979, then in 1992, 1995, 2000, and 2007. Saturn, Uranus, Neptune, comets, and asteroids also received missions. Mercury, after the first encounter, was left alone for about 30 years. The reason was not that Mercury was considered boring or fully understood. The first mission, Mariner 10, only flew past and mapped roughly 40 to 45% of the surface. Instead, the problem was practical. Mercury is one of the most difficult planets in the solar system to reach and then orbit. Its environment and its position in the sun's gravity well both create serious challenges. As mentioned earlier, Mercury lives in a kind of furnace. Its surface can reach temperatures of about 430 degrees Celsius near the hottest areas. Any spacecraft going there must be able to endure intense heating from both the sun and the planet below. At the same time, flying inward toward the sun means falling deeper into the sun's gravity well. A probe launched toward Mercury accelerates more and more as it approaches the inner solar system. To slow down enough to be captured into orbit around Mercury, the spacecraft has to shed a large amount of orbital energy. Trying to do all of that only with rocket fuel is like trying to swim upstream in a very fast river. The sun's gravity is constantly pulling, and the spacecraft's engines can only push back so much. Extra fuel adds extra mass, and mass is one of the main constraints in spacecraft design. A heavier spacecraft requires a larger launch vehicle to escape Earth's gravity, which makes the mission more expensive. Fuel also takes up space and mass that could otherwise be used for scientific instruments. Engineers aim to keep spacecraft as light and efficient as possible, carrying only the propellant truly needed. For many years after Mariner 10, mission planners could not find a way to put enough fuel on a Mercury orbiter to slow it into orbit and still have room for a useful payload of instruments. As a result, after the flybys of 1974 and 1975, active exploration of Mercury paused. The planet remained partially mapped and poorly sampled while attention shifted elsewhere. In 1985, however, an orbital mechanics specialist named Chen Wang-Yen proposed a different approach. Rather than relying mainly on rocket thrust to slow the spacecraft, she described a trajectory that would use the gravity of several planets and the geometry of repeated flybys to gradually remove orbital energy. The idea was not to head straight for Mercury and brake hard, but to take a longer, more complex route around the inner solar system. Under this plan, a spacecraft would orbit the Sun many times. Along the way, it would swing past Earth once, Venus twice, and Mercury 3 times before finally being slow enough to be captured into orbit around Mercury on the 4th close pass. During each flyby, the probe would skim past the planet and exchange momentum with it. This gravity assist process slightly changes the spacecraft's speed and direction without using extra fuel. Some flybys could also include minor braking due to atmospheric drag, depending on altitude. Over time, these small changes would add up. The full path, Yen suggested, involved about 15 orbits around the Sun and a total travel distance of roughly 7.9 billion kilometers. The journey would take on the order of 6.5 years from launch to final orbital insertion at Mercury. It was a long, carefully choreographed spiral inward, rather than a direct plunge. At first, her proposal did not immediately lead to a mission, but as mission costs and design limits were studied in more detail, the value of this trajectory became more clear. By 1998, NASA began to seriously explore the idea of a dedicated Mercury orbiter based on such a flight path. The concept was eventually developed into a mission called MESSENGER, short for Mercury Surface, Space Environment, Geochemistry, and Ranging. The spacecraft was launched in 2004. MESSENGER was relatively small by NASA deep space standards. The main body was about 1.88 meters long and about 1.3 meters wide, with a mass of roughly 1,100 kilograms at launch. For comparison, the Juno spacecraft sent to Jupiter is about 20 meters long when its solar arrays are extended. To survive its mission, MESSENGER carried a high-thrust main engine, a ceramic cloth heat shield to protect it from intense sunlight, 2 solar panel wings for power, and a suite of scientific instruments. These instruments included cameras, spectrometers, and fields and particles sensors designed to study Mercury's surface composition, geology, magnetic field, exosphere, and interior. During its first year after launch, MESSENGER completed 1 orbit around the Sun and returned to the vicinity of Earth. This Earth flyby served as both a gravity assist and a systems check, Engineers used the opportunity to test its instruments on a familiar target. The spacecraft took images of Earth and the Moon and collected data on our atmosphere and magnetosphere. These measurements could be compared with well-known reference values, making it easier to check for any instrument errors or calibration issues. The results looked good, and the mission continued further inward. As Messenger traveled closer to the Sun, mission planners used an additional subtle tool to manage its speed: solar radiation pressure. Sunlight is made of photons, and when photons strike a surface, they transfer a tiny amount of momentum. Over long timescales, this can act like a very gentle push. By adjusting the angle of its solar panels, Messenger could use them a bit like sails, catching or shedding a small amount of radiation pressure. While the force involved was very small at any one moment, the long duration of the cruise phase allowed this effect to contribute meaningfully to the overall energy balance, saving propellant and fine-tuning the approach. In 2006, Messenger made its first flyby of Venus. The geometry of this encounter, however, placed the spacecraft on the far side of the Sun as seen from Earth, which meant there was no direct radio contact during the closest approach. The spacecraft still captured some images and other data stored on board, but it could not send real-time information back at that moment. In 2007, Messenger flew past Venus again. This time, another mission, the European Space Agency's Venus Express, was already in orbit around the planet. Together, the two spacecraft were able to coordinate overlapping measurements, providing simultaneous observations of Venus's environment from different vantage points. This allowed scientists to study the particles and fields near Venus in a way that a single probe could not. After those inner flybys, Messenger moved on toward its main target. The spacecraft made its first flyby of Mercury on the 14th of January 2008. That encounter, and the second flyby that followed, went according to plan, providing new images and data from regions of the planet never seen before. During the third flyby in 2009, however, the spacecraft experienced a problem and went into what is known as safe mode. Safe mode is a protective state built into many spacecraft. If onboard computers detect a condition outside expected ranges, they can automatically power down non-essential systems, point the spacecraft toward the Sun for power and warmth, and wait for further instructions. During this third Mercury flyby, Messenger had to pass through the shadow of the planet for about 18 minutes, which meant its solar panels could not generate power and it had to rely on its batteries. A configuration issue in the power management software led the computer to trigger safe mode. For several hours, mission controllers could not operate the spacecraft as planned. Once Messenger emerged from Mercury's shadow and sunlight again charged its panels, the system reset and normal operations were restored. The mission resumed its trajectory, completing one more orbit around the Sun before the final approach. On the 11th of March, 2011, after its long and complex journey, Messenger fired its main engine and entered orbit around Mercury. The chosen orbit was highly elliptical. At its closest, the spacecraft passed about 200 kilometers above the surface. At its farthest, it was about 15,000 kilometers away. This elongated orbit served several purposes. It reduced the thermal load on the spacecraft by limiting the time spent very close to the hot surface, and allowed different regions of the planet to be studied under various lighting conditions. Near Mercury, not only is the Sun up to about 7 times brighter than it appears from Earth, but the planet itself radiates heat back into space, acting like a warm mirror. Moving farther away during parts of the orbit allowed the spacecraft to cool. Each orbit took about 12 hours. Over time, this pattern let Messenger systematically cover the entire globe, building up detailed maps and datasets. The original plan called for a 1-year primary mission in orbit. However, the spacecraft performed well, and mission extensions were approved. In the end, Messenger remained in orbit for about 4 years, far longer than first expected. Before launch, scientists had hoped that Messenger might return at least 1,000 images of Mercury. In practice, it exceeded that goal by a wide margin. Over the course of its mission, it captured more than 200,000 images. These images, together with other measurements, provided a complete, high-resolution color map of Mercury's surface and also recorded views of nearby comets and neighboring planets during flybys. By late 2014, the spacecraft's supply of propellant, which had been carefully conserved through the years, was nearly exhausted. Messenger's orbit had gradually been lowered through planned maneuvers and gravitational effects until it was skimming only about 25 kilometers above Mercury's surface at closest approach. On the 25th of December 2014, controllers used the remaining fuel to adjust the orbit one last time and extend the mission as much as possible. Eventually, with propellant fully depleted, there was no way to counter the slow orbital decay caused by Mercury's gravity and solar influences. On the 30th of April 2015, Messenger impacted the surface of Mercury on the far side of the planet, ending a mission that had lasted more than a decade and had covered billions of kilometers of travel through the inner solar system. During its operational life, Messenger carried several key instruments that deepened our understanding of Mercury. One of them was a magnetometer, designed to measure the strength and direction of the planet's magnetic field. Data from this instrument helped map the structure of Mercury's magnetosphere and provided clues about the interior. Evidence suggests that Mercury's magnetic field is generated by a dynamo process in a molten outer core, similar in principle to Earth's, but with important differences. On Earth, the combination of relatively rapid rotation and tidal interactions with the moon help keep the core in motion and maintain the dynamo. Mercury, by contrast, rotates slowly and has no large moon. It does, however, have a strongly eccentric orbit. Its distance from the Sun changes significantly over the course of each year. As Mercury moves closer to and farther from the Sun, the strength of the Sun's gravity and the associated tidal forces change. These changing tides can flex the planet slightly, causing internal friction and helping to keep parts of the core in a liquid state. This ongoing motion can sustain a magnetic dynamo even in a small, slowly rotating planet. Messenger's measurements also showed that Mercury's magnetic field is not centered. It appears to be offset northward from the planet's center by about 20% of the planetary radius. The reasons for this asymmetry are not yet fully understood and remain an active area of research. The overall strength of the magnetic field at the surface is only about 1% of Earth's field. Even so, it significantly affects how the solar wind interacts with the planet. Because Mercury is so close to the Sun, the solar wind pressure in its neighborhood is much stronger than at Earth's orbit. A weak field, combined with strong solar wind, means that Mercury's magnetosphere is small and compressed close to the surface. By comparison, Earth's magnetosphere extends many planetary radii outward on the day side. Mercury's magnetosphere, though small, is highly dynamic. It responds quickly to changes in the solar wind. One important process in this environment is magnetic reconnection. Magnetic reconnection occurs when magnetic field lines from different regions are pushed together by the solar wind and rearrange. In this process, field lines can break and join in new ways, releasing energy and allowing charged particles to cross boundaries that would otherwise confine them. Messenger observations indicated that reconnection events at Mercury are about 100 times more frequent than similar events in Earth's magnetosphere. When reconnection happens at Mercury's dayside boundary, some solar wind particles gain access to the magnetosphere and are guided along field lines into the planet's magnetotail, the elongated region of magnetic field and plasma extending away from the Sunday H. Computer simulations of this region show streams and swirls of plasma moving in response to these reconnection events. The flows you see in these simulations within the plasma region are the result of reconnection events. In addition to the magnetic reconnection and plasma flows, Messenger found another striking feature in Mercury's space environment. The spacecraft repeatedly detected bursts of energetic electrons, each carrying hundreds of thousands of electron volts of energy. Over the course of its mission, Messenger recorded thousands of these events. Most of them were clustered in the northern hemisphere and pushed close to the planet on the side facing the Sunday. This pattern is not yet fully understood. Current ideas suggest that these electrons are accelerated when magnetic fields in the magnetotail break and reconnect, then travel along magnetic field lines from the southern polar region toward the north. Messenger also carried several spectrometers. A spectrometer is an instrument that studies how matter interacts with light. By examining the light reflected or emitted from a surface, it can reveal which elements and minerals are present without needing a physical sample. Spectrometers can also analyze particles in a thin atmosphere. Mercury does not have a true atmosphere like Earth, but it does have an exosphere, a very tenuous envelope of atoms and molecules, so thin that its particles almost never collide. What Messenger found about the link between this exosphere and the surface surprised scientists. Mercury is not just a baked, lifeless rock stripped of lighter materials. Its surface is rich in volatile substances, meaning materials that can more easily turn into gas or escape when heated. The spacecraft detected relatively high amounts of potassium, magnesium, sulfur, sodium, and chlorine. These appeared to be more abundant than on any other rocky planet, and much more abundant than on our moon. The ratios of these volatile elements on Mercury resemble those on Mars more than those on Earth or Venus. This came as a serious challenge to earlier models of how the inner solar system formed, because many of those models predicted that a small, hot world like Mercury should have lost most of its volatile elements long ago. These materials at the surface are constantly exposed to strong radiation from the sun, especially near the equator. That radiation can knock atoms free or heat them enough to escape into the exosphere. This may help explain why certain elements, such as potassium, appear more common in some regions, for example in parts of the northern hemisphere, than around the equator. Near the equator, higher temperatures make it easier for volatile atoms to leave the surface. Over long periods of time, more potassium would have been driven off into space from those hotter areas. The exosphere itself contains many of the same particles seen in surface materials, including sodium and potassium. It is not a fixed shell. It is constantly being eroded and replenished. Charged particles from the solar wind can pick up and carry away ions from the exosphere. Pressure from sunlight can push neutral atoms outward as well. Without any source of replacement, Mercury would lose this thin envelope in a relatively short time compared with the age of the solar system. Most of the material in the exosphere does, in fact, come from the surface through processes like sputtering by solar wind, micrometeorite impacts, and thermal release. However, Messenger also detected elements in the exosphere that are not present on the solid surface in significant amounts. Two of these are hydrogen and helium. These are the main components of the Sunday, the solar wind, a stream of charged particles flowing out from the sun carries hydrogen and helium throughout the solar system. Near Mercury, some of this solar wind becomes trapped for a time in the exosphere, adding hydrogen and helium to the mix. As far as we know, this is the main source of those two elements around the planet. Images and measurements from MESSENGER showed other elements in the exosphere as well. For example, calcium was observed, with a pattern that changes over the course of a Mercury day. For reasons still under study, calcium appears more abundant near dawn than near dusk. Magnesium has been seen streaming away from the night side, contributing to the thin tail of material that stretches out behind the planet. This tail of escaping atoms has actually been known for some time. Ground-based telescopes on Earth had already detected sodium atoms glowing as they flow away from Mercury, giving the planet a faint, comet-like appearance. If you could stand on the night side of Mercury and look up, the sky would not be completely dark. You might see a very faint yellowish glow from sodium in the tail, a bit like the distant lights of a city seen through haze. The intensity of this tail changes with Mercury's position in its orbit. Because the orbit is eccentric, the distance to the Sun and Mercury's speed both change over a Mercury year. Observations show that the strongest sodium emission tends to occur when Mercury is at an intermediate distance from the Sun, not at its closest or farthest points. MESSENGER also found water-related species in Mercury's exosphere, including water vapor. This was unexpected for such a hot, airless world. The water molecules could come from passing comets, which release gas and dust as their icy surfaces warm near the sunday. Another likely source is the water ice stored in cold traps near Mercury's poles. Small amounts of that ice can be liberated and move into the exosphere as vapor. The idea of water ice on Mercury might sound surprising, given how hot the equatorial regions can become. But the poles tell a different story. Radar observations from Earth, including those made with the Arecibo radio telescope, revealed regions near the poles that reflect radio waves strongly. These bright radar patches suggested deposits of water ice. When MESSENGER imaged those same polar areas, the bright radar regions matched floors of craters that never see direct sunlight. In these permanently shadowed craters, temperatures stay low enough for water ice to remain stable over long periods of time. Estimates based on these measurements suggest that Mercury may hold on the order of 250 kilograms of water ice, mostly locked in these cold traps. By Earth standards, this is not a vast amount, but for any future robotic or human operations on Mercury, it would be a valuable resource. Having a local supply of water would reduce the need to bring all water from Earth. MESSENGER's images also revealed unusual small depressions scattered across many areas of the surface. These features, called hollows, seem to be unique to Mercury. They look like clusters of shallow, rimless pits with bright, fresh-looking interiors. They do not resemble impact craters. Instead, they appear to form when volatile materials in the near-surface rock are lost, possibly by sublimation, leaving behind empty spaces that collapse. Mercury's strong sunlight and lack of atmosphere may make this process particularly effective. The hollows also appear relatively young, suggesting that this is an ongoing, active geological process even today. Beyond hollows, the mission provided clear views of ancient lava plains, volcanic vents, and craters altered by past flows of molten rock. Some large impact basins show evidence that, after the initial impact, heat and magma from below reshaped their interiors. MESSENGER also documented long, curved cliffs called lobate scarps. These are thought to form as the planet cools and its interior contracts, causing the outer crust to wrinkle and thrust upward in some places. By mapping these scarps, Scientists estimate that Mercury's diameter has shrunk by more than 14 kilometers since its formation. That is more contraction than expected for a small planet, and it tells us that Mercury's interior cooled and changed in significant ways. All of these discoveries have been very important for planetary science. Without Messenger, our picture of Mercury would still be mostly guesses based on a few flyby images. Yet the mission remains relatively unknown outside scientific circles. Another mission, Bepi Colombo, a joint project of the European and Japanese space agencies, is now on its own long journey to Mercury. Its planned arrival around the middle of the 2020s is expected to add even more detail and may bring wider public attention to this small but complex world. To understand how extreme Mercury's past may have been, it helps to think about how rocks behave at very high temperatures. Mercury today is extremely hot by human standards. Daytime temperatures can reach about 430 degrees Celsius, similar to the temperatures in some wood-burning fires. Dust and rocks on the surface are heated close to their physical limits. It is not the hottest planet in the solar system. That role belongs to Venus, with its thick atmosphere trapping heat, but Mercury is still among the hottest places with a solid surface. Over time, Mercury has cooled compared with its earliest days. The presence of ice at the poles and the evidence of contraction show that the interior has lost heat. Earlier in its history, however, conditions would have been even more intense. When solid rock is heated enough, its crystal structure breaks down and it becomes molten. The molten material beneath the surface is called magma. Magma is very thick compared with water. Its viscosity can be 10,000 to 100,000 times greater than that of liquid water. For comparison, it can be similar in thickness to tomato ketchup, though, of course, at much higher temperature, and not something you would ever want near food. Depending on the composition of the rock, magma typically forms at temperatures starting around 600 degrees Celsius and can require up to about 1,300 degrees Celsius. For Mercury's crust to partially melt and form magma, regions of the planet must have reached at least those temperatures in the past. Once magma reaches the surface and flows as lava, it can travel long distances despite its thickness. As lava cools, the outer layer solidifies and insulates the hotter material inside, allowing the interior to continue moving downslope under gravity. We see the results of such flows on Mercury in several craters. One example is a structure known as Raditlati. This crater is thought to be relatively young, perhaps less than 1 billion years old, because its walls are well preserved and its floor has relatively few overprinting impacts. Raditlati is more than 25 kilometers across. The terrain just outside the crater is rugged, with hills and rough blocks. Inside, by contrast, the floor is smooth and gently curved. This contrast is unlikely to be accidental. The most straightforward explanation is that, after the crater formed, lava flooded the interior. Originally, the floor would have been as broken as the surrounding landscape. Over time, molten rock filled the basin and then cooled, leaving behind a flat, even surface. Lava tends to settle into the lowest available areas and spreads out until it reaches a nearly level state, similar to how water in a container seeks a flat surface under gravity. Where did this lava come from? Scientists consider two main options. One possibility is that the impact that created Raditlati fractured the crust, providing pathways for magma from deeper layers to rise up slowly and fill the basin. This would be a form of impact-triggered volcanism. The second possibility is that the impact itself heated the existing surface layers so strongly that they partially melted, creating what is called impact melt. In that case, the lava would be melted crust rather than magma from deeper reservoirs. In reality, both processes may have contributed, some magma rising from below and some crust melting in place. Once we learn to see a smooth crater floor as a sign of past lava, similar patterns become obvious elsewhere. Other craters on Mercury, such as Rustaveli, Copland, Polygnotus, and Rachmaninoff, show plains of smooth material with isolated peaks or central mountains poking through. In Rachmaninoff, for instance, the central region contains a bright, relatively smooth inner ring with cracks and ridges radiating and circling within it. These patterns suggest that magma rose beneath the surface and lifted the crust, then cooled and shrank, leaving wrinkled and fractured textures. In such places, the sequence seems to be: an impact excavates a basin, fractures the crust, and possibly heats it. Magma or melted rock fills part of the basin. As the lava cools, it contracts and breaks, forming concentric and radial features. Mercury's changing surface temperature, with its long, hot days and equally long, cold nights, may further stress these cooled lava surfaces and contribute to their cracking. Not all lava on Mercury is confined to craters. In some regions, there are signs of broad flows that traveled across the landscape like slow-moving rivers. A valley known as Angkor Vallis, for example, shows evidence that molten rock moved from higher ground to lower basins, filling depressions along the way. These large-scale flows spread out to form extensive plains. Over time, such plains acquired a distinct, slightly orange tint in color images. Researchers now use this subtle color as a clue that an area was shaped by volcanic activity rather than only by impacts. One area to the northeast of Rachmaninoff crater illustrates this well. When MESSENGER flew over this region late in its mission, it captured detailed high-resolution images. The surface there appears to be coated by a fine, loose layer of material. Careful analysis of the patterns and context suggests that this material is volcanic ash, tiny fragments of rock and glass, ejected during explosive eruptions. Instead of flowing as thick rivers of lava, this kind of eruption sends clouds of hot particles outward, which then settle over the terrain. NASA scientists, looking at this blanket of fine, bright material spread over darker ground, compared it to a landscape dusted with a strangely luminous, burning form of snow. On early Mercury, it would not only have been rivers of lava beneath your feet that mattered, but also hot ash falling from above during explosive eruptions. That ash would have settled over wide areas, changing the color and texture of the ground. And those were only some of the gentler signs of volcanism. Other features point to eruptions so powerful that they appear to have removed entire blocks of crust. One example is a feature called Navoi. At first glance, it looks like a large crater. However, its shape does not match what we expect from a typical impact. When a meteorite hits a solid surface that is not hot enough to melt into a deep pool of lava, the impact usually forms a bowl-shaped cavity with a central peak. The process is similar from crater to crater. The incoming object strikes, excavates a hole, and throws material outward. The steep walls of the new cavity are unstable. Under gravity, loose rock and soil slide down toward the center from all sides. The material from opposite walls meets in the middle with a lot of momentum. With nowhere else to go, that energy pushes the material upward, forming a peak. A helpful way to picture this is to think about throwing a large stone into a pond. Water rushes inward to fill the hole where the stone entered. When water from opposite sides collides, it shoots upward in a secondary splash. Rock does not flow as easily as water, So instead of a brief splash, the uplifted material remains as a permanent central mountain. Depending on the angle at which the meteorite arrived, this central structure may be nearly round or a bit elongated, but it has a recognizable form. Navoi does not fit this pattern. Its inner structure is irregular, and the central formation is not shaped like a typical impact peak. When scientists examined its shape and the distribution of nearby debris, they concluded that Navoi is more likely the result of a giant volcanic explosion than a simple impact. In this scenario, magma and gas built up beneath the surface until the pressure became too great. When it was released, the eruption tore out a cavity roughly 66 kilometers across, blasting rock outward for many kilometers around. The power needed to excavate such a hole and scatter its contents over that distance must have been enormous. Putting these pieces together, an image of early Mercury takes shape. At that time, the planet would have experienced frequent meteoroid and asteroid impacts, some of them large enough to melt crustal rock. Volcanic vents would have produced slow, steady outflows that formed wide lava plains, and also violent eruptions that hurled ash high into space. Gases released in eruptions would have been dense and toxic, even if they did not stay long as a true atmosphere. The ground in some regions might have been stable for long periods. In others, it could have been disrupted from below with very little warning. This was the phase when parts of the planet were literally melting and refreezing. Today, Mercury is quiet. As far as we can tell, there are no active volcanoes left. The surface still heats up strongly under sunlight, but the internal activity that once drove widespread volcanism has largely faded. The crust has cooled enough to contract and crack rather than flow. Still, for those who study the landscape carefully, the record of that more violent era remains written in the layers of rock, the plains, the craters, and the ridges. The planet's scars are the clues we use to reconstruct its early history. Because Mercury is so hard to reach, collecting these clues has never been simple. In all of human history, only 2 missions have visited it directly so far: Mariner 10 in the 1970s, and Messenger, which entered orbit in 2011. A third mission, Bepi Colombo, is on its way and scheduled to arrive in the mid-2020s. Of these, only Messenger has orbited Mercury and mapped its surface in detail. Many of the strange shapes seen in its images are still not fully understood years later. Others have already helped us understand the powerful processes that shaped the early inner solar system. When we look at Mercury's surface in those images, a few things stand out right away. One is the planet's color. To the unaided eye, or in simple photographs, Mercury can look gray, but in enhanced color and careful processing, it shows speckled tones of gray, cream, and beige, with lighter and darker regions, and narrow bright streaks. The darker areas are thought to be rich in graphite, a form of carbon also used in pencil lead. The lighter patches and streaks are linked to different materials and processes that we will touch on as we move through its features. The next striking feature is the sheer number of craters. Like the Moon, Mercury has been bombarded by countless bits of rock and ice over billions of years, with no thick atmosphere to burn up incoming debris, and no active weather or plate tectonics to erase old scars. Most impacts leave permanent marks. Craters overlap each other, and their distribution is roughly even across the globe. From them, we can piece together a timeline of impacts and surface evolution. One way to estimate the relative age of a crater is to study the sharpness of its rim and the condition of its inner walls. A crater with crisp, sharply defined edges and steep walls is likely to be relatively young. Over long periods, Thermal cycles, micrometeorite impacts, and other slow processes soften these features. Older craters have more rounded rims and more subdued interior details. Sometimes, a younger crater forms right on top of an older one, creating a layered pattern. By comparing overlapping craters, we can tell which events happened first. The differences between older degraded craters and younger fresh ones also tell us something important about Mercury's surface. It is not completely static. Even without a thick atmosphere, wind, or flowing liquid water, the crust can still change shape over time. As mentioned earlier, Mercury's interior has cooled, and as it does, the outer shell contracts. This causes the surface to crumple, forming long scarps where one block of crust is thrust over another. In other places, we see evidence that crater walls have slumped or collapsed. In one example, about a quarter of the crater rim remains crisp and intact, while the remaining 3/4 have broken away and slid downward, forming a low, irregular slope into the crater floor. The material there seems to have moved under its own weight. Researchers are not yet sure why only part of the rim failed. It could be that the rock properties were different in that sector, or that the structure was weakened by pre-existing fractures, or that the impact angle created uneven stresses. For now, this remains an open question. These partial collapses, along with the global system of scarps, show that Mercury's crust is slowly adjusting and smoothing over geological time. Details are erased in some spots and preserved in others, giving the surface a mix of very old and moderately younger features. Another pattern visible on Mercury is the presence of bright, radial streaks associated with certain craters. These are called ray systems. Similar rays exist on the Moon, but on Mercury, some of them are particularly large and prominent. Rays appear as thin, light-colored lines spreading outward from a central crater, sometimes for hundreds of kilometers. Their lighter color suggests that they consist of material excavated from beneath the darker, graphite-rich surface and scattered across the surrounding terrain during an impact. For a long time, scientists had difficulty reproducing ray patterns in laboratory experiments. Test impacts into sand or powder usually produce circular blankets of ejecta with smoothly fading edges, not the thin, streaky lines seen from orbit. Many different combinations of projectile size, speed, and angle were tried. The rays remained hard to mimic. In 2018, a researcher named Tapan Sabuwala came across an online video made by a student group performing their own impact experiments. In their setup, small projectiles were dropped into trays of granular material. To Sabuwala's surprise, the students had managed to produce ray-like streaks similar to those seen on Mercury and the Moon. The key difference between their experiment and earlier official tests was simple. The students had not smoothed the surface beforehand. In most prior lab work, scientists carefully leveled and prepared the target material to make conditions more controlled. The student project left the sand rough, with bumps and irregularities. When Sabuwala and colleagues repeated the experiments with an unsmoothed, rough surface, they found that impacts into that rough terrain naturally produced thin radial streaks. The roughness guided the flow of ejected material into channels, creating ray patterns. This result suggested that the presence and fine structure of ray systems depend mainly on the shape and texture of the surface that is struck, rather than on impact speed, impact angle, or exact material composition. Knowing this, we can better appreciate how energetic some of Mercury's impacts must have been. Earlier, we mentioned rays that stretch a few hundred kilometers. Those are relatively small. The ray system associated with a crater named Hokusai for example, extends almost all the way around the planet. Mercury's circumference is about 15,000 kilometers, so those rays span a very large fraction of the globe. Another crater, Debussy, has a ray system that covers over 1,000 kilometers. Although the moon also hosts rays, many of Mercury's systems are larger and more extensive. These giant ray systems tell us that Mercury has been struck by very large projectiles traveling at high speed. Because Mercury orbits so close to the Sun, objects falling inward under the Sun's gravity reach high velocities by the time they cross its path. The planet's own gravity is relatively weak and does not easily capture passing objects into stable orbits as moons. Instead, many objects are either deflected past or collide with the surface at very high speed. This is one reason why mission planners must work carefully when sending spacecraft there. The region is dynamic, and the Sun's influence dominates, yet even strong impacts, ray systems, and volcanic plains cannot account for every structure we see. One of the most intriguing areas on Mercury is a crater named Apollodorus and the surrounding system of fractures known as Pantheon Fossae. At first glance, Apollodorus appears to be a circular depression with some unusual cracks radiating outward. Many craters show fractures and faults, but here they are, particularly striking. The pattern of narrow troughs and ridges around the crater looks a bit like a spider web or like cracked glass seen from above. The resemblance to shattered glass is not accidental. Glass tends to break in sharp, branching lines because it is hard and brittle. When a crack starts, the stress at its tip drives it forward along paths where the material cannot deform easily, so the fracture runs and branches in characteristic ways. Most other craters on Mercury do not show the kind of fractured pattern seen around Apollodorus. Elsewhere, the crust usually responds to impacts by forming clean circular basins and sometimes ray systems, where material is sprayed outward in streaks. That behavior is what we expect from a surface made mostly of loose or semi-fractured rock and dust. Dry sand, for example, does not crack into sharp patterns when struck. It simply splashes and settles. On Mercury, outside this region, we do not see anything that looks like a network of glass-like fractures. That is why Pantheon Fossae stands out. It suggests that something unusual happened here. One idea is that the crust in this area might have been especially cold and stiff at the time of deformation, making it brittle. Mercury's nights can drop to around -180 degrees Celsius, which could, in theory, make rocks more prone to cracking. But if that alone were the cause, we would expect to see similar fracture systems in other regions that also cooled to low temperatures. On the night side, we do not. Looking more closely, there is another odd detail. The crater Apollodorus, which sits near the center of the pattern, is not exactly at the geometric center of the radiating troughs. It is close, but slightly offset. That raises the possibility that the fractures of Pantheon Fossae formed first due to some internal process, and that the crater was created later by a separate impact that happened to occur nearby. In that case, Apollodorus would not be the cause of the fractures, only a later mark placed on top of an older feature. If the fractures were not created by an impact from above, they may have been caused by forces from below. One idea is that a pulse of magma, or a rising plume in the interior, pressed upward on the crust, causing it to crack radially, like dried mud pushed from beneath. Another suggestion is that the area experienced complex tectonic stress as the planet cooled and shrank, focusing strain into this region. At present, There is no single accepted explanation. Pantheon Fossae remains one of Mercury's open puzzles, a pattern that clearly records strong forces in the crust, but does not yet tell us exactly which process created it. This sense of mystery is part of what makes Mercury so interesting. Many of its features have only recently been seen for the first time, and it will take time to fully understand them. A new mission, Bepi Colombo, launched by the European and Japanese space agencies, is on a long trajectory toward Mercury and is expected to arrive around the middle of the 2020s. Once in orbit, it will study the planet's magnetic field, exosphere, surface, and interior in more detail than before. Until those data arrive, scientists continue to analyze the rich set of observations from MESSENGER, looking for new patterns and testing ideas. Meanwhile, Mercury continues to orbit close to the Sun, enduring intense heat and steady bombardment by particles and occasional impacts. It has existed in this harsh environment for billions of years and will likely remain there for billions more. Its dark, heavily cratered surface, shaped by impacts, volcanism, contraction, and space weathering, is a record of survival under extreme conditions. Reaching it with spacecraft is difficult, but the planet itself has never left its place in the inner solar system. There is still much to learn from it. When we turn our attention outward to the next planet, the contrast is striking. Venus, the second planet from the Sun, appears soft and almost serene when seen from a distance. It is wrapped in a bright, unbroken cloud layer that gives it a smooth, creamy appearance in telescopes. From that view alone, it is easy to understand why ancient observers associated it with a goddess of love and beauty. Beneath that cloud blanket, however, conditions are very different. The surface of Venus is extremely hot, shaped by widespread volcanism and covered by a thick atmosphere that presses down with crushing force. Temperatures are high enough to melt many metals. The air is filled with carbon dioxide and clouds of sulfur compounds. It is one of the most hostile environments known in our solar system. Despite this, we have learned quite a lot about it through remote sensing and a few brief landings by robotic probes. To place Venus in context, it helps to recall its basic orbit. Venus is the second planet from the Sun and Earth's nearest planetary neighbor. Its average distance from the Sun is about 0.72 astronomical units, which corresponds to roughly 108 million kilometers. Unlike Mercury, Venus follows an almost perfectly circular path. Its orbit is the least eccentric of any planet, meaning its distance from the Sun changes very little over the course of a Venus year. At its closest approach to Earth, Venus comes to within about 41 million kilometers of us. At that time, it is closer than any other planet can be. Curiously, this is not when it appears brightest in our sky. When Venus is at its closest, it lies between Earth and the Sun, and we see mostly its night side. Even then, some light can scatter through its atmosphere and make it visible, but the illuminated portion is small. Venus is actually brightest to us when it shows a thinner crescent phase at a position where it is somewhat farther from Earth, but a larger fraction of its daylit side is visible. During these times, Venus can outshine every night sky object except the Moon. Its intense, steady light near the horizon or high in the twilight sky has often confused casual observers. There are many reports of unidentified flying objects that, upon closer examination, turned out to be Venus. Even a former United States president, Jimmy Carter, reported seeing a strange object in the sky in 1969. Later analysis suggested that the bright object was most likely Venus. Viewed through a small telescope, Venus shows phases like the Moon, crescent, half, and gibbous. Seeing its sharp crescent edge can be particularly striking. Since Venus orbits between Earth and the Sun, it is natural to ask whether it ever passes directly across the Sun's face from our viewpoint. It does, but such transits are rare. They occur in pairs, with two events separated by about 8 years, and each pair is separated from the next by more than a century. The most recent transit of Venus occurred in 2012. The next will not happen until the year 2117. This rarity arises because Venus's orbit is slightly tilted compared with Earth's. For a transit to occur, Venus must be between Earth and the Sun, and also be crossing the plane of Earth's orbit. The timing involved is very specific. Like all the planets, Venus follows the general direction of orbital motion around the Sun, moving counterclockwise when viewed from above the Sun's north pole. Its rotation, however, is unusual. While most planets rotate in the same sense as they orbit, Venus rotates in the opposite direction. This is called retrograde rotation. It also spins extremely slowly. Venus takes about 243 Earth days to complete one full rotation relative to the distant stars. This is its sidereal day. Its orbital period around the Sun, its Venusian year, is about 224 Earth days. So, on Venus, a sidereal day is actually longer than a year. Because of its retrograde spin, the length of a solar day, meaning the time from one noon to the next, as seen from the surface, is different from the sidereal day. On Venus, the solar day is about 117 Earth days. That means that over the course of one Venus year, you would experience just under 2 full cycles of daylight and darkness. The rotation is so slow that at the equator, the ground moves at only about 6.5 kilometers per hour relative to the planet's axis. This slow spin and nearly spherical shape make Venus one of the roundest objects in the solar system, second only to the Sunday. The reason for its backward rotation is still debated. Possible explanations include a giant impact early in its history that changed its spin, long-term tidal interactions with the Sun, or complex exchanges of angular momentum between the atmosphere and the solid planet. So far, there is no single, definitive answer. In terms of basic size and mass, Venus is very similar to Earth. That is why it is often called Earth's sister or twin planet. It is one of the 4 inner terrestrial or rocky planets. Venus's diameter is about 12,100 kilometers, a little smaller than Earth's diameter of about 12,740 kilometers. Its average density is about 5.3 grams per cubic centimeter, compared with Earth's density of about 5.5 grams per cubic centimeter. As a result, the surface gravity on Venus is only slightly lower than on Earth. A person who weighs 100 kilograms on Earth would weigh about 90 kilograms on Venus. In physical terms, the surface gravity on Venus is around 8.9 meters per second squared. From there, however, the similarities end. The atmosphere of Venus is extraordinarily thick and heavy. The pressure at the surface is about 92 times the pressure at sea level on Earth. That is roughly what you would experience 1 kilometer below the surface of Earth's oceans. The mass of gas surrounding Venus is about 93 times greater than the mass of Earth's atmosphere, all compressed into a slightly smaller volume. The atmosphere is made mostly of carbon dioxide, with small amounts of nitrogen and trace gases. High above the surface, a global cloud deck forms. These clouds are rich in sulfur dioxide and contain droplets of sulfuric acid. Together, the dense atmosphere and reflective clouds create the strongest greenhouse effect known on any planet in our solar system. Sunlight can enter the upper layers, but infrared heat from the surface has great difficulty escaping back into space. The result is an average surface temperature of about 462 degrees Celsius. That is hot enough to melt lead and many other metals. It also makes the surface of Venus hotter than the surface of Mercury. Even though Mercury is closer to the Sun and receives more direct solar energy, Venus receives only about 25% of the solar radiation that Mercury does. But its thick atmosphere traps heat so efficiently that it becomes the hotter world. Because the heat cannot easily escape, temperatures on Venus are fairly uniform, day and night, equator and poles. The surface stays at roughly the same extreme temperature. The small axial tilt of Venus, only about 3 degrees, means there are almost no seasonal swings in sunlight. The climate is harsh, but steady, always hot, always under crushing pressure. Near the ground, wind speeds are modest, on the order of a few kilometers per hour. However, because the air is so dense, even slow winds exert a strong force. They can push small rocks and dust along the surface. In contrast, at the cloud tops, the winds are much faster. Speeds of around 300 kilometers per hour have been measured there. These high-altitude winds circle the planet roughly every 4 to 5 Earth days. This rapid super-rotation makes the cloud layer appear to move much faster than the solid planet underneath. The clouds themselves sit above the lower, denser carbon dioxide atmosphere and contain sulfur dioxide and sulfuric acid droplets. Sulfuric acid is highly corrosive. Any rain formed from these droplets would be extremely dangerous to equipment or structures. In practice, most of the acid droplets evaporate before they can reach the surface due to the high temperatures and pressure in the lower atmosphere. Even so, their presence adds another layer to the already harsh conditions on Venus. The clouds of Venus are extremely bright. They reflect most of the sunlight that reaches them, letting only about 10% pass through to the lower atmosphere and the surface. Because this cloud layer wraps completely around the planet, it hides the ground from view in ordinary visible light. From space, you see only the featureless blanket of cloud, not the rocks beneath it. These clouds are not only reflective, they are also active. Observations show that they can produce lightning, much like storm clouds on Earth, although lightning on Venus seems to occur less often. More recently, scientists have discovered that Venus has a large atmospheric vortex at its south pole. In some ways, this recalls the famous polar vortex on Saturn, but the two are not identical. Images show Venus on one side and Saturn on the other. Saturn's polar region is dotted with many separate storms, each a distinct dark spot with a larger vortex at the center. Venus, in contrast, shows a single, complex, swirling structure. This polar vortex on Venus is found at an altitude of about 59 kilometers, just above the main cloud deck. This brings us to an interesting point about the vertical structure of Venus's atmosphere. Around 50 kilometers above the surface, the pressure and temperature are surprisingly similar to conditions at sea level on Earth. At that height, a thermometer and a barometer would record values that would be quite tolerable for humans. The gravity there is also close to Earth's gravity. The difficulty is not the temperature, pressure, or gravity, but the chemistry of the air. The gas is mainly carbon dioxide with droplets of sulfuric acid. For a human to exist there, they would need a sealed environment, such as an airtight balloon or aircraft. Inside such a vehicle, the outside conditions at that altitude would otherwise be remarkably Earth-like. To understand the surface itself, we can turn from orbital views to images taken from the ground. In the 1960s through the 1980s, Soviet missions made a series of pioneering attempts to land on Venus. Earlier probes failed before touchdown, but in 1970, Venera 7 became the first spacecraft to land on another planet and return data from its surface. It probably tipped over on impact, so its information was limited, but it still managed to transmit a surface temperature of about 475 degrees Celsius. Later, Venera 8 confirmed that visibility at the surface is not completely blocked. The main cloud layers end at high altitude, so near the ground the air can be clear enough for cameras. With a visibility of roughly 1 kilometer, Venera 9 sent back the first black and white image from the surface of Venus. Over the following years, Venera 10, 13, and 14 returned more photographs, including color images and measurements of temperature, pressure, and rock composition. These brief landings gave us our only direct views of the Venusian landscape: broken rocks, flat plates, and a horizon under a heavy, yellowish sky. Since then, several orbiters have used radar to map the surface from above. Radar signals can penetrate the clouds and bounce off the ground, allowing spacecraft to build up detailed, high-resolution maps of the terrain. These radar maps show that Venus is covered by many large volcanoes and volcanic structures. There are at least 167 volcanoes with diameters greater than 100 kilometers. On Earth, only the island of Hawaii forms a volcanic complex on that sort of scale. This does not mean Venus is currently more volcanically active than Earth. Instead, it reflects differences in how their crusts evolve. Earth's lithosphere is broken into moving plates. Over tens to hundreds of millions of years, plate tectonics recycles the crust, creates new ocean floor, and subducts old material back into the mantle. This process helps vent internal heat and refresh the surface. Venus appears not to have active plate tectonics. Its crust seems to act as a single, global shell. Estimates based on crater counts and surface features suggest that much of the Venusian crust is around 300 to 600 million years old. Many scientists propose that at some point in that time frame, there was a global or near-global resurfacing event. In this scenario, the mantle beneath the crust heated up, partially melted, and pushed large volumes of magma upward, flooding much of the surface with lava. Today, about 80% of Venus's surface consists of solidified lava plains. On top of these plains, there are hundreds of thousands of smaller volcanic structures of various shapes and sizes. In addition to volcanoes, radar mapping has identified about 900 impact craters. None of these craters are smaller than about 3 kilometers in diameter. This is because Venus's dense atmosphere destroys or slows smaller incoming bodies. Objects less than roughly 50 meters across tend to break up and burn in the thick air before reaching the ground. Turning from the surface back to the space environment, we reach the topic of Venus's magnetic behavior. Despite having a mass and size similar to Earth, Venus does not have a strong global magnetic field like Earth's. This was a surprise when spacecraft measurements first revealed it. The lack of a significant internal magnetic field means that Venus does not have a large, protective magnetosphere generated by a core dynamo. There are several ideas about why this might be the case. Both planets are thought to have metallic cores, but perhaps the conditions inside Venus are different. One hypothesis suggests that Earth's magnetic field may have been influenced by a major impact early in its history, the same event that likely led to the formation of the Moon. The energy and mixing from that impact could have helped organize or sustain the flow of molten metal in Earth's outer core. If Venus did not experience a similar event, its core may have cooled or stratified in a way that does not support a strong dynamo. This is still an area of active research. Although Venus lacks an intrinsic dipole field like Earth's, its interaction with the solar wind still produces an induced magnetosphere. The solar wind compresses the upper atmosphere and creates currents that, in turn, generate magnetic fields. High-energy particles and radiation from the sun directly affect the upper layers of the atmosphere. These interactions can drive lightning in the clouds and cause gradual loss of lighter molecules. Over time, the solar wind strips away some of the upper atmosphere, especially lighter components, forming a long tail of ionized gas trailing behind Venus. Under certain alignments, when Earth and Venus are in conjunction on the same side of the Sun, this extended tail can reach into the region of space near Earth, though it is far too diffuse to see by eye. The story of Venus is also a story of exploration. From Earth's surface, we see only a bright point or a crescent in the sky. In more recent decades, we have used radio, radar, infrared, ultraviolet, and in situ probes to study it more deeply. Early on, progress was difficult. Interplanetary missions require precise navigation and robust engineering. During the early years of the space age, especially in the 1960s, many attempts to reach Venus failed before arrival or lost contact. Out of 15 early missions between 1961 and 1967, only a few achieved their main goals. Mariner 2 and Mariner 5 from NASA successfully flew by and studied the planet's atmosphere. Venera 4 from the Soviet program became the first to send data from within the Venusian atmosphere. Subsequent Venera missions, including Venera 4, 5, and 6, performed atmospheric entry and returned information on pressure, temperature, and composition as they descended. In late 1970, Venera 7, as mentioned earlier, achieved the first soft landing on another planet and transmitted data from the surface, even if only briefly. These missions laid the groundwork for our current understanding of Venus's atmosphere and surface. To visualize how extreme the atmosphere is, we can mentally follow a probe like Venera as it falls toward the planet. Far from Venus, the spacecraft travels through near vacuum. As it approaches, it turns its instruments toward the planet and prepares for entry. The upper atmosphere begins around 250 kilometers above the surface and extends down to about 60 kilometers. At these heights, the air is very thin. Only about 1% of the total atmospheric mass lies above this region. The probe encounters only a fine haze. In many ways, this part of the descent is similar to passing through the upper layers of Earth's atmosphere at comparable altitudes. Low-density gas, significant temperature differences between day and night, and little direct mechanical stress on the spacecraft. However, the composition is quite different. Instead of mostly nitrogen and oxygen, the gas is dominated by carbon dioxide. Even here, temperatures at these heights can range from around -37 degrees Celsius to -43 degrees Celsius, depending on local time and conditions. For the probe, this is still a relatively gentle environment compared with what lies below. One interesting phenomenon at high altitude is known as airglow. In Venus's upper atmosphere, some oxygen atoms emit infrared radiation as they transition between energy states. This glow can be detected by instruments sensitive to infrared light. Images taken by spacecraft like Venus Express show the upper atmosphere shining faintly in specific infrared wavelengths. often displayed as bluish hues in processed pictures. These emissions give scientists clues about chemical reactions and energy flows at the edge of space. As the probe continues downward, it reaches the main cloud deck around 60 kilometers above the surface. This is the layer that dominates pictures of Venus in visible light. The clouds extend from roughly 60 kilometers down to about 40 kilometers. They are thick and opaque in most wavelengths we see with our eyes. Within this region, ultraviolet light from the sun breaks apart carbon dioxide into carbon monoxide and single oxygen atoms. These free oxygen atoms then react with sulfur dioxide and water vapor present in small amounts to form droplets of sulfuric acid. These sulfuric acid droplets, along with other aerosols, make up the bulk of the cloud particles. Here, the environment becomes more hostile. The probe encounters corrosive droplets and increasingly strong winds, yet it still cannot see the ground. The clouds continue to block any direct line of sight. From orbit, this cloud deck reflects roughly 1/3 of the sunlight that strikes Venus, contributing to its unusual brightness. Ice-like particles of sulfuric acid and other compounds are highly reflective, so they send much of the incoming solar energy back into space. Combined with the thick carbon dioxide layer beneath, this helps explain why Venus is such a brilliant object for both satellites and ground-based observers. To go beyond what Venera could see, modern instruments use infrared wavelengths. In visible light, the clouds appear as smooth, mustard yellow blankets. In thermal infrared images, the scene looks very different. Observations from spacecraft like Japan's Akatsuki show bright and dark bands, vortices, and wave patterns in the atmosphere. The bright regions often correspond to warmer, deeper layers, while the dark regions mark cooler clouds higher up. These views make the three-dimensional structure of the atmosphere more obvious. Infrared images also reveal clearly that the lower atmosphere is extremely hot. Carbon dioxide is efficient at trapping heat. The dense carbon dioxide layer near the surface glows strongly at certain infrared wavelengths, making the whole planet appear bright in those bands, with the sulfuric acid clouds above showing up as darker patches overlaying the hot background. For a probe descending through these layers, the experience would grow harsher with each kilometer. Sulfuric acid droplets would coat and attack its exterior surfaces. In the upper clouds, winds can reach around 100 meters per second, roughly 360 kilometers per hour, carrying the probe sideways relative to the ground. These winds encircle the planet much faster than Venus itself rotates, making the atmosphere super-rotate around the globe. At altitudes of about 50 to 55 kilometers, the temperature ranges from around 25 degrees Celsius to 75 degrees Celsius, depending on location. The pressure is similar to pressure at sea level on Earth, but as the probe continues downward past the bottom of the cloud deck, it enters a region of clearer but much denser air. Here, the pressure increases rapidly. The carbon dioxide becomes so compressed that it no longer behaves like a simple gas. Instead, it enters a supercritical state, somewhere between a liquid and a gas. In this state, the distinction between phases blur. The fluid can have the density of a liquid, but flow more like a gas. In the lower atmosphere, the winds slow to only a few kilometers per hour relative to the surface. The air is so dense that motion through it would feel like moving through water, but water heated to about 464 degrees Celsius. It is an environment where even metal components are pushed near their limits. Only specially designed landers can function there, and even they can survive for only a short time. Images from missions like Galileo, which captured Venus's lower atmosphere in near-infrared light around 2.3 micrometers, show how intensely the lower atmosphere radiates heat, with bright areas marking hot regions and darker areas where thick clouds above block the infrared emission. The structure of Venus's atmosphere, thin upper layers, thick cloud decks, and supercritical lower regions, forms a stack of distinct physical and chemical regimes. To highlight the differences among these layers, scientists often compare images taken in different parts of the spectrum. One useful way to do this is to look at the atmosphere under ultraviolet light, where contrasts in cloud composition and dynamics stand out even more clearly. Ultraviolet images from spacecraft have added another layer to this picture. Data from a Japanese mission show Venus's clouds at wavelengths of about 283 and 365 nanometers. These views do not show as much strong contrast as the infrared images, but they still reveal more variation than ordinary visible light. In the ultraviolet, patches of darkness and mottled regions appear across the cloud tops. These darker areas suggest that something in the clouds is absorbing ultraviolet light instead of reflecting it. The exact substance, or mix of substances, responsible for this absorption is still under debate. It is a reminder that there are still chemical components in Venus's atmosphere that we have not fully identified or understood. The poles of Venus are another source of puzzles. Infrared images of the north and south polar regions show large vortices, each roughly the size of a continent such as Europe. These giant whirlpools of gas are driven by the fast winds in the upper atmosphere, which can blow at around 100 meters per second. The strange part is that each polar vortex often shows not one central eye, but two, forming a kind of double structure. The detailed shapes of these vortices are complex and change on timescales of less than a day. They are difficult to model accurately, and scientists are still working to understand exactly how they form and evolve. Once a probe passes through the atmosphere and reaches the surface, the view changes again. Because the clouds block all direct lines of sight from orbit in visible light, the only true photographs of the Venusian ground in visible wavelengths come from landers that actually touched down. So far, there are only a handful of such images, taken by 4 Soviet Venera probes. These pictures show that the air near the ground is clearer than many had feared. Instead of a thick, obscuring haze, the landscape is visible out to about a kilometer. The light is a dull yellow, tinted by the composition of the atmosphere. The terrain itself is rocky and barren, with flat plains and scattered blocks. The pattern of cracked slabs and relatively smooth areas suggests ancient lava flows that have cooled, solidified, and then been altered by the intense heat and pressure over long periods. There is no sign of liquid water. Everything appears very dry, which fits with the extreme temperature at the surface. Some researchers have suggested that, far in the future, if the sun brightens enough and Earth experiences a runaway greenhouse effect, our planet might develop surface conditions that resemble those on Venus today. The Venera landers could only endure these conditions for a short time. Each lasted at most a couple of hours before its electronics failed under the combined stress of roughly 90 times Earth's surface pressure and temperatures of several hundred degrees Celsius. Even so, the data they sent back provided a crucial first look at Venus from ground level. Although these images are decades old, they remain our only direct photographs from the planet's surface. To gain a more complete view of the planet's geography and topography, scientists rely on radar. Neither visible light, ultraviolet, nor most infrared wavelengths can penetrate the thick cloud cover deeply enough to give clear images of the ground. Radar, on the other hand, can be transmitted from a spacecraft, bounce off the surface, and return with information about elevation and texture. In the early 1980s, The Soviet Venera 15 and Venera 16 orbiters used radar to map parts of Venus at resolutions of about 1 to 2 kilometers. In the early 1990s, NASA's Magellan mission improved on this dramatically. Between 1990 and 1994, Magellan mapped about 98% of the surface, with a resolution down to about 120 meters. The radar images from these missions are striking. They show a planet dominated by volcanic plains, large shield volcanoes, dome-like structures, long fracture zones, and prominent impact craters. The relative lack of very old, heavily cratered terrain and the pattern of lava flows suggests that the surface is geologically young on average, perhaps a few 100 million years old, likely renewed by widespread volcanic events. Composite maps that combine data from Venera, Pioneer Venus, and Magellan present a detailed picture of mountains, valleys, craters, trenches, and plateaus. Radar imaging has been essential in revealing this hidden landscape beneath the clouds. Even with all this information, many questions remain. One of the most discussed recent topics has been the possible detection of phosphine gas in Venus's atmosphere. In 2020, measurements from the James Clerk Maxwell telescope were interpreted as showing trace amounts of phosphine high in the clouds. Phosphine can be produced by several processes, including industrial activity and certain high-temperature reactions. But one pathway on Earth involves microbes living in low-oxygen environments. The idea that a gas associated with life on Earth might be present on Venus, even in tiny quantities, drew a lot of attention. However, follow-up studies by other teams using different instruments and analysis methods did not confirm the original signal. By 2022, reviews by groups including NASA concluded that there was no strong evidence for phosphine in the Venusian atmosphere at the levels first claimed. It seemed likely that the initial interpretation had been mistaken. Then, in 2023, Jane Greaves, the original lead researcher, reported new observations suggesting the presence of phosphine deeper in the atmosphere. The results are still being examined and debated. Future missions with dedicated instruments will be needed to provide a clear answer to this question. Beyond phosphine, there are broader mysteries. Venus and Earth are similar in size, mass, and basic composition. Yet their surface conditions and atmospheres are dramatically different. Why did their histories diverge so sharply? Did Venus ever have significant amounts of liquid water on its surface? If so, how long did it last? And what processes removed it? What is the detailed chemical makeup of the atmosphere at different heights and of the surface rocks in different regions? Answers to these questions could help us understand not only Venus, but also the limits of habitability for rocky planets in general. After a period when Venus received less attention than some other targets, interest has grown again. Several missions are now planned or proposed for the coming decade from different space agencies and organizations. These include projects from the United States, Europe, Russia, China, India, and at least one private venture focused on searching for possible signs of life high in the atmosphere. New orbiters, probes, and possibly balloons could carry instruments designed to sample the clouds, refine maps of the surface, and measure the planet's interior structure more accurately. Studying Venus across many wavelengths, visible, infrared, ultraviolet, radio, and radar, has already taught us far more than visible light alone ever could. We have used radar to identify volcanoes and craters through kilometers of cloud spectroscopy to infer atmospheric and surface chemistry, and thermal infrared imaging to see how heat is trapped and distributed. These tools help explain why Venus is so extreme. They also keep open the question, however unlikely, of simple microbial life in some niche environment high above the deadly surface. As striking as all of this is, we do not have to travel far to find a world that is both scientifically rich and deeply familiar. Earth, our home, remains the most complex and dynamic planet we know. It has liquid water on its surface, an atmosphere rich in oxygen, and a strong magnetic field that shields it from much of the solar wind. Most importantly, it is the only place we know that hosts life. Even so, there is still a great deal we do not fully understand about how our planet works and how it has changed over time. To begin to describe Earth, it helps to clear up a common idea. You may have heard people say that Earth is pear-shaped or egg-shaped. This can give a misleading picture, as if our planet were strongly distorted. The truth is more subtle. Earth is not a perfect sphere, but the deviations from a sphere are small compared with its overall size. Earth is slightly squashed rather than perfectly round. It is wider at the equator than at the poles by about 45 kilometers. This small bulge is caused by the planet's rotation. As Earth spins, centrifugal effects push material outward more strongly at the equator. Because of this, the point on Earth's surface that is farthest from the planet's center is not the summit of Mount Everest, but the peak of the Chimborazo volcano in Ecuador, which sits closer to the equatorial bulge. On average, Earth's diameter is about 12,742 kilometers. For a long time, people have tried to understand where Earth fits in the universe. Was everything in the sky revolving around us, or were we moving around the sun? And more simply, was the world flat or curved? The idea of a round Earth was already discussed by Greek thinkers as early as the 6th century before the Common Era. Around 240 before the Common Era, Eratosthenes made a famous estimate of Earth's size. He heard that at noon on the summer solstice in Syene, in southern Egypt, the sun shone straight down a well with no shadow. In Alexandria, farther north, the sun still cast a shadow at the same time. By measuring the angle of that shadow and knowing the distance between the two cities, he was able to estimate Earth's circumference to within about 5 to 10% of the modern value, using only geometry and simple observations. Centuries later, in the 16th and early 17th centuries, the picture of our place in the solar system changed again. Nicolaus Copernicus proposed a model in which Earth and the other planets orbit the Sunday. Johannes Kepler refined this with precise mathematical laws of planetary motion, and Galileo Galilei used telescopic observations to support the idea. Together, their work helped establish the heliocentric model. The Sun, not Earth, is at the center of the planetary system. Today, building on that legacy and many other contributions, we know that Earth is the third planet from the Sun and one of 4 inner rocky or terrestrial planets. Earth orbits the Sun at an average distance of about 150 million kilometers. At its closest point, called perihelion, it is about 147 million kilometers from the Sunday. At its farthest point, aphelion, it is about 152 million kilometers away. One full orbit takes about 1 year, as we define it. However, our common time units are not as simple as they might seem. Earth does not complete its orbit in exactly 365 days, but in about 365 and 1/4 days. To keep our calendar in step with the seasons, we add an extra day every 4 years. That is why we have leap years. Months, in principle, relate to the moon's motion. The word month is closely linked to moon. The moon takes about 27.3 days to complete one orbit around Earth, but our 12-month calendar does not use this period directly. It would be hard to fit months of exactly 27.3 days into a year of about 365.25 days without creating awkward leftover fractions, so calendar systems have historically used more convenient lengths. Even the day is not as simple as 24 hours. A sidereal day, which is the time it takes Earth to rotate 360 degrees relative to distant stars, is about 23 hours, 56 minutes. This is 4 minutes shorter than the 24-hour solar day we use in daily life. The reason is that Earth is not only spinning, it is also moving along its orbit. After Earth has rotated once relative to the stars, it has shifted a bit along its path around the Sunday to bring the sun back to the same position in the sky as the previous day. Earth must rotate a little more, which takes about those extra 4 minutes. That extra rotation is what defines the solar day. The situation is a bit more complicated because Earth's orbit is slightly elliptical and its axis is tilted. As a result, the length of a true solar day can vary by up to tens of seconds over the course of a year. To keep things simple, we use a mean solar day, an average value of 24 hours, for our clocks. On longer time scales, the rotation rate changes as well. Tidal interactions between Earth and the Moon gradually slow Earth's spin. The length of the day increases by roughly a couple of milliseconds per century. Hundreds of millions of years ago, days were shorter. Models suggest that about 500 million years ago, a day would have been under 22 hours long, and there would have been roughly 400 such days in a year. You can see Earth's rotation by watching the night sky with a fixed camera. In time-lapse images, stars appear to move in arcs across the sky, circling around points near the celestial poles. Earth's motion around the sun and the tilt of its axis also cause the sun's position at the same clock time to shift slightly over the year. A visual way to show this is through an analemma, a composite photograph of the sun, taken from the same location at the same time of day over many days throughout a year. The points trace out a figure-8 shape in the sky. The up and down motion in this pattern comes from Earth's axial tilt, which causes the sun to appear higher in summer and lower in winter. The side-to-side motion is related to the slight eccentricity of Earth's orbit and the difference between true solar time and mean solar time. If you made an analemma on other planets, each one would look different. The shape depends on that planet's tilt, orbital eccentricity, and rotation period. For Earth, the axis is tilted by about 23.5 degrees relative to the plane of its orbit. This tilt is the main reason we have seasons. The changes in temperature between summer and winter are not primarily due to the small change in distance to the sun over the year. Being a few million kilometers closer or farther does not matter much when the average distance is about 150 million kilometers. If distance were the dominant factor, we would expect the season with the greatest warmth to occur near perihelion. In fact, perihelion occurs in early January during northern hemisphere winter. The larger effect comes from the angle at which sunlight strikes the surface and the length of the day. When the sun is high in the sky, its rays are concentrated on a smaller area, delivering more energy per square meter. When the sun is low, the same amount of energy is spread over a larger surface area, reducing the heating. In summer, the sun's path is higher, days are longer, and a given location receives more total energy over the day. In winter, the sun's path is lower, days are shorter, and heating is reduced. This pattern, controlled by axial tilt, shapes climate zones and seasonal cycles. Above Earth's surface lies the atmosphere, a thin shell of gas, compared with the size of the planet, but crucial for life. By composition, the lower atmosphere is mostly nitrogen, about 78%, and oxygen, about 21%. Argon makes up about 1%. There are also trace amounts of other gases, such as carbon dioxide, and small quantities of methane and other compounds. Water vapor is present as well. Its concentration can vary widely from almost 0 up to several percent, but on average, it is around 1%. The atmosphere plays many roles. Oxygen supports the metabolism of most complex life. Carbon dioxide is used by plants in photosynthesis. The air slows and burns up many small meteoroids before they can reach the ground. It helps moderate temperature differences between day and night and between regions, without any greenhouse effect from gases like water vapor and carbon dioxide. Earth's average surface temperature would be much colder, well below freezing. With the natural greenhouse effect, the global average is around 15 degrees Celsius, which allows liquid water to be stable over large parts of the surface. Within the atmosphere, there is also a layer richer in ozone, a molecule made of 3 oxygen atoms. This ozone layer absorbs much of the sun's harmful ultraviolet radiation, particularly the shorter wavelengths that can damage DNA and other biological molecules. Without this shield, conditions at the surface would be far more dangerous for many forms of life. The atmosphere supports the water cycle, a key system for Earth's climate and biosphere. When the sun heats the surface, liquid water from oceans, lakes, and moist ground evaporates and rises as water vapor. As this moist air moves and cools, the water vapor condenses onto tiny particles in the air, forming clouds. These clouds can travel long distances carried by winds. Eventually, the water falls as rain, snow, or other forms of precipitation. Surface runoff and rivers then return water to the oceans, completing the cycle. Along the way, flowing water shapes the landscape through erosion and provides a medium for life, from microscopic organisms to plants and animals. Earth's hydrosphere, its total water, especially the oceans, is central to its character. The mass of the oceans is only about 1 part in 4,400 of Earth's total mass, but their influence is huge. If you could magically smooth out all mountains and fill in all basins, the entire planet would be covered by a global ocean, almost 3 kilometers deep. In reality, the surface is far from smooth. There are continents, deep ocean trenches, mid-ocean ridges, and mountain ranges. This varied relief is due in large part to plate tectonics, one of Earth's defining features. The outer shell of the planet, the lithosphere, is broken into plates that move slowly over the hotter, more ductile mantle beneath. Where plates collide, one may be forced under another, creating subduction zones, deep trenches, and volcanic arcs. Where plates pull apart, magma rises to create new crust, as at mid-ocean ridges, where plates slide past each other, faults form and earthquakes occur. These processes build mountains, open and close oceans, and recycle materials between the surface and interior over tens to hundreds of millions of years. From a human perspective, earthquakes, volcanic eruptions, and tsunamis associated with plate boundaries can be dangerous and destructive in specific regions. On geological timescales, however, plate tectonics helps renew and reshape the surface. It exposes fresh rock to weathering, influences the long-term carbon cycle, and may help stabilize climate by regulating carbon dioxide over millions of years. This ongoing renewal keeps Earth's surface dynamic and, in many ways, hospitable for life over very long spans of time. Beneath Earth's moving plates and hot mantle lies the core, made mainly of iron and nickel. This deep interior is the main reason Earth is the densest planet in the solar system, with an average density of about 5.5 grams per cubic centimeter. The core is large compared with those of many other planets. The liquid outer core extends to a diameter of roughly 5,000 kilometers. At the very center lies the inner core, which is thought to be solid despite its high temperature, because the pressure there is enormous. Pressures in the inner core reach on the order of 360 gigapascals, and temperatures are estimated to be close to 6,000 degrees Celsius. Similar to the surface of the Sunday, the outer core is hot enough to remain liquid, and its moving, electrically conducting fluid is what generates Earth's magnetic field. As the molten metal circulates, it converts kinetic energy into electrical currents, which in turn produce a large-scale magnetic field around the planet, somewhat like a giant bar magnet tilted relative to the rotation axis. This magnetic field is crucial for life at the surface. It guides most of the charged particles in the solar wind around Earth, rather than letting them strike the atmosphere directly. Without it, bursts of energetic particles from solar storms would regularly reach low altitudes, damaging living tissue and gradually stripping away the atmosphere over long periods. With the field in place, many of those particles are diverted toward the polar regions, where they interact with the upper atmosphere and produce auroras. On Earth, the most common auroral color is green, caused mainly by excited atomic oxygen high above the surface, emitting light as it returns to lower energy states. Another distinctive feature of Earth is its large natural satellite, the Moon, also called Luna. Many planets have moons, but Earth's moon is unusually large relative to its host planet. This gives it a prominent place in our sky. On a clear night, the moon's disk is bright enough that we can see major dark and light patches on its surface without any instruments. Its presence, however, is not only aesthetic. The moon's gravity exerts a steady pull on Earth's oceans, raising tides. As Earth rotates under this gravitational influence, the oceans form bulges that move around the globe. The solid crust also flexes slightly, though the effect is much smaller and not as obvious. These tidal forces have other consequences. Over long times, they transfer angular momentum between Earth's rotation and the moon's orbit, gradually slowing Earth's spin and moving the moon farther away. Some models suggest that the constant tug of the moon may also influence how active Earth's plate tectonics are, though this connection is still being studied. In any case, the combination of a large moon, an active core, plate tectonics, an atmosphere, and abundant liquid water is unusual among known planets. When we step back and consider all these factors together, the internal structure, magnetic shield, oceans, active crust, and stable energy from the sun, it is striking how many conditions have to align for a planet to support complex life. On Earth today, more than 8 billion humans share the planet with countless other species. We are able to ask questions about our origins and our place in the wider cosmos using tools and knowledge built up over generations. From orbit, images show Earth as a blue, white, and green sphere with swirling clouds and dark landmasses. For now, it is the only world we know that is both physically welcoming and biologically active on a large scale. Beyond Earth, many people wonder whether any other place in space could ever feel as hospitable. We do not yet know the answer. To explore this question, one useful step is to examine the other rocky planets in more detail. Among them, Mars has drawn particular interest. Mars is one of Earth's nearest planetary neighbors and has long attracted attention in both science and imagination. It is often portrayed as a possible home for alien life or a future destination for human explorers. Over the past few decades, orbiters, landers, and rovers have mapped its surface and taken high-resolution images, revealing a rugged landscape with a reddish tint and a wide range of geological features. In some ways, Mars is less foreign than it might first appear. One similarity is the length of its day. A solar day on Mars, known as a sol, is about 24 hours, 39 minutes, and 35 seconds, only slightly longer than a day on Earth. The Martian year, however, is longer, about 1.88 Earth years, or roughly one Earth year, plus 320 days and a few additional hours. This longer year is expected for a planet farther from the Sun, with a wider orbit. Mars and Earth also have similar axial tilts. Earth's axis is tilted by about 23.5 degrees, while Mars's tilt is around 25 degrees. Because of this, Mars has seasons that are broadly similar to Earth's, summers and winters in each hemisphere. The temperatures, however, are colder overall and vary over a broad range. In polar winter, temperatures can drop to around -43 degrees Celsius or lower. During equatorial summer days, temperatures can rise up toward about 35 degrees Celsius in some locations. These values depend on local conditions and time of day. Like Earth, Mars has polar caps. During each hemisphere's winter, that pole is in continuous darkness, and the air above it cools dramatically. Unlike Earth, a significant fraction of the thin carbon dioxide atmosphere can freeze out directly onto the surface as dry ice, forming seasonal layers on top of permanent caps that are mostly water ice. As spring returns and sunlight returns, the carbon dioxide ice sublimates, turns directly from solid into gas, and re-enters the atmosphere. The size of the polar caps grows and shrinks over the Martian year. Images show striking spiral patterns in the ice at both poles. These spirals are thought to result from interactions between wind, sublimation, and the Coriolis effect, which is linked to the planet's rotation and causes moving air and ice to curve. When large amounts of carbon dioxide sublimate in a short time, they can drive strong winds. In some cases, sublimation of dry ice at the poles can produce wind speeds up to about 400 kilometers per hour. These winds can lift and move fine dust across the surface, influencing the Martian dust cycle and contributing to storms and haze that sometimes cover large areas of the planet. There are important differences between Mars and Earth as well. Mars is smaller, with a diameter of about 6,779 kilometers, compared with Earth's 12,742 kilometers. It is also less dense. Combined, these factors mean that surface gravity on Mars is weaker than on Earth. The gravitational acceleration at the Martian surface is only about 38% of Earth's. If an object has a weight of 100 kilograms on Earth, it would weigh about 38 kilograms on Mars. Experiments and demonstrations show that objects fall more slowly on Mars than on Earth, and people or robots there could jump higher for the same effort. Interestingly, the surface gravity on Mars is similar to that on Mercury, even though Mercury's diameter is only about 4,879 kilometers. This highlights how dense Mercury must be compared with Mars. The lower gravity on Mars allows for very large geological structures. One of the most striking is Olympus Mons, the tallest volcano and one of the tallest mountains in the solar system. Only the central peak associated with the Resilvia Basin on the asteroid Vesta is considered higher if measured from the base of its crater floor. Olympus Mons rises about 3 times higher than the elevation difference between sea level and the summit of Mount Everest. In round numbers, Olympus Mons reaches roughly 22 kilometers above the surrounding plains. In addition to its height, Olympus Mons is extremely broad. Its base spans more than 600 kilometers across. The volcano is a shield volcano, built by repeated lava flows with low viscosity that spread over wide areas. Because of this, its slopes are gentle, with an average incline of only about 5 degrees. Standing on the summit, you would not see the entire mountain. The curvature of Mars and the gentle slope would hide the flanks from view. Around the edge of the volcano lies a steep escarpment, a cliff that can be up to 8 kilometers high in places. Near the summit, a complex of overlapping collapse craters, or calderas, marks locations where the surface has sunk following the withdrawal of magma from underlying chambers. Another remarkable feature on Mars is Valles Marineris, a vast canyon system that runs along the equatorial region. In global images, it appears as a deep, dark scar stretching across a large portion of the planet's face. Valles Marineris is about 3 times as long as Earth's Grand Canyon and roughly 4 times as deep, making it one of the largest known canyon systems in the solar system. When you picture Mars, one of the first things that probably comes to mind is its color. The planet's surface has a distinct reddish tone, which is why it is often called the red planet. This color comes from the chemistry of its rocks and dust. Mars's crust contains a lot of iron-bearing minerals. Over long periods of time, these minerals reacted with small amounts of oxygen to form iron oxide, essentially rust. The fine dust and weathered rock coated in these iron oxides give the ground and boulders a reddish-brown hue. Close-up images from landers and rovers show this clearly. The soil looks like dry, reddish sand, and many rocks have a rusty coating. The level of detail in these photographs is remarkable. They let us see pebble-sized features, cracks, and layering as if we were standing there, something astronomers of the past could only imagine. Looking at such dry landscapes, it is easy to assume that Mars is a quiet, unchanging world. In reality, the planet is still active in several ways, especially at the surface and in the atmosphere. One striking example comes from an avalanche observed in 2008 by an orbiter. As the spacecraft passed over a steep scarp, it caught an image of material collapsing down a slope. The falling debris kicked up a bright cloud of dust. In that view, the dunes below were hundreds of meters tall, and the photographed area spanned only a few kilometers. Even so, the dust plume was large and obvious, showing that slopes can still fail and reshape small patches of the surface today. In polar regions, another unusual pattern appears. Some images show dark, branching shapes spread across lighter terrain, often nicknamed spiders. These structures can be tens of meters to nearly a kilometer across. They are not living organisms, but their appearance is spider-like in outline. They form through seasonal carbon dioxide processes. In winter, carbon dioxide from the atmosphere freezes out as a layer of dry ice, sometimes up to about a meter thick. In spring, sunlight penetrates the translucent ice and warms the darker ground underneath. Gas builds up at the base of the slab until it finds a weak spot and vents upward. The escaping gas carries fine, dark material, which falls back to the ground around the vent in radial patterns. Over time, repeated events carve and stain the surface, leaving those spider-shaped marks. Recent images from orbiters such as the ExoMars Trace Gas Orbiter have captured these features in fine detail, showing how they emerge and change over seasonal cycles. They are one of several signs that carbon dioxide, ice, and gas play an active role in shaping parts of the Martian polar landscape. Dunes on Mars also evolve. By taking repeated images of the same dune fields over months and years, scientists have seen ridges shift, slip faces migrate, and patterns sharpen as winds move sand. In some sequences, dark streaks appear where fresh material has slid down a slope and bright dust has been removed. New impact craters have also been documented. When a meteoroid strikes, it can excavate subsurface layers. In a few cases, the impact has exposed buried water ice. In one notable example, a fresh crater revealed bright material around its rim and in its ejecta. Over time, the exposed ice sublimated away, confirming that it had been water ice near the surface. Mars is also famous for its dust. The planet's thin, dry atmosphere and fine surface material make it prone to large dust storms. When strong winds blow across dusty regions, they lift particles into the air, forming large clouds and sometimes walls of dust that can spread across continents or even encircle the entire planet. Spacecraft images have recorded storms so large that they are easily visible from orbit. In one case, in 2012, an image showed a bright, swirling dust cloud. A week later, a follow-up view revealed that the storm had thinned and faded. Polar views occasionally show storms crossing over the caps, leaving temporary haze and streaks. On a smaller scale, narrow, twisting tracks on the surface mark the paths of dust devils. These are spinning columns of air similar to small tornadoes. As they move, they can lift bright dust and leave behind darker ground. Some have been imaged from orbit as tall, thin plumes, with shadows stretching for kilometers. Estimates suggest that certain dust devils can reach heights of hundreds of meters, with column diameters of a few tens of meters. Rovers on the ground have also recorded dust devils passing nearby, capturing short sequences where the air fills with fine particles and the lighting changes. All of this activity might suggest that Mars has a thick atmosphere, but that is not the case. The air on Mars is extremely thin compared with Earth's. To experience a similar pressure here, a person would have to climb to an altitude well above typical airplane cruising levels, closer to about 35 kilometers or more, where breathing becomes impossible without assistance. On Mars itself, the surface pressure is less than 1% of Earth's at sea level. The atmosphere is composed mostly of carbon dioxide, about 96%, with small amounts of nitrogen, argon, and trace gases. Anyone on the surface would need a pressure suit and an oxygen supply. Despite its thinness, the atmosphere is thick enough to scatter sunlight and create weather patterns, including clouds, dust storms, and hazes. It is also capable of producing beautiful sunsets. Cameras on rovers have captured scenes where the sun sinks toward the horizon and the sky near the sun turns a soft blue due to the way fine dust particles scatter different wavelengths of light. Evidence from dried river channels, delta deposits, and mineral types shows that Mars once had a much thicker atmosphere. In that earlier time, liquid water could flow on the surface, carving valleys and pooling in lakes or shallow seas. Today, with the air so thin and cold, liquid water cannot remain stable for long at the surface. A key factor in this change is Mars's weak or absent global magnetic field. Billions of years ago, Mars likely had an active core dynamo that produced a stronger magnetic field. At some point, that dynamo shut down or weakened dramatically. Without a robust magnetosphere, The upper atmosphere became more exposed to the solar wind. Over billions of years, energetic particles from the sun have stripped away lighter atoms and ions from the outer layers of the atmosphere. Spacecraft such as MAVEN have detected streams of ionized atmospheric particles flowing away from Mars into space, directly illustrating this loss process. The result is the thin, cold atmosphere we observe now. Mars also has two small moons, Phobos and Deimos. They are irregularly shaped, more like captured asteroids than large, round moons. Compared with Earth's moon, they are tiny. In the Martian sky, Phobos appears as a lumpy, fast-moving object, while Deimos looks more like a bright star. The difference in apparent size is partly due to distance. Earth's moon orbits at about 384,400 kilometers from Earth. Phobos orbits only about 6,000 kilometers above the Martian surface. You could fit several Earths between Earth and its moon, but only about one Mars between Mars and Phobos. Deimos orbits much farther out than Phobos and is smaller. From Mars, it appears as only a point of light, though still moving steadily against the background stars. Both moons add to the character of the Martian sky, and their motions can be predicted and used to study Mars's gravity field and internal structure. Occasionally, the alignment of Mars, its moons, and the Sun creates a kind of partial eclipse. Rovers have recorded Phobos passing directly in front of the Sun, blocking part of its light. In these sequences, the Sun's disk is briefly carved into a jagged shape by Phobos's irregular outline. The light level drops slightly, and shadows change in subtle ways. These events are short because Phobos moves quickly in its low orbit, but they offer a unique perspective, an eclipse seen from another world. From Mars, Earth can also be seen as a bright point in the sky. In some images taken by spacecraft, Earth appears as a tiny pale dot, sometimes with the moon visible nearby as an even fainter point. At distances of tens of millions of kilometers, our planet is just another star-like speck. All of human history, every landscape and ocean, lies on that small light. These views remind us that, while Mars looks like a distant red point from Earth, our own world looks just as small when seen from Mars. Mars, with its rusty plains, towering volcanoes, deep canyons, polar spirals, and restless dust, is one of the most compelling places in the solar system for future exploration. Its similarities to Earth make it easier to imagine walking on its surface, while its differences challenge our understanding of how planets form, evolve, and sometimes lose their air and water.